Have you ever heard of a chip without silicon? That's right. For the first time, engineers have managed to create a functional processor without using a single drop of silicon. And more than that, it not only works, it may be the fastest and most efficient chip ever built. It sounds like science fiction, but it's pure science and it could change everything. Since the 1960s, silicon has dictated the pace of technological progress. It's the foundation of computers, cell phones, satellites, rockets, smart refrigerators, and even our coffee machines. But silicon is reaching its limit. This isn't about engineering anymore. It's physics, it's quantum mechanics. It's the moment when atoms stop obeying our rules. And right at this point, a heavy, colorful crystal with a psychedelic look entered the radar of science. As electrons start slipping through walls, chip miniaturization has hit a critical point. Today we're working at 3 nanometers, soon 2, and then less. But here's the problem. At that scale, traditional electronics start breaking their own laws. Literally transistors, those tiny switches that turn signals on and off inside chips, become so small that they behave like quantum systems. And that changes everything. Imagine trying to close a door, but the wind still passes through. That's what happens with electrons. They start tunneling, a quantum phenomenon where particles pass through barriers that should be solid. It's like walking through a wall. Inside a chip, this ruins control. Signals leak, data scrambles, and performance collapses. This quantum limit threatens to silence silicon forever. No matter how much engineering improves, nature has drawn a line. That's why scientists began searching for something new, not just a replacement, but a completely different path. And that's when an old element from the periodic table started to shine: bismuth. At first glance, it looks like a lab ornament, heavy metal, strange geometric shapes with a psychedelic rainbow glow. But behind that eccentric look lies atomic behavior that challenges everything we know about semiconductors. Bismuth has a rare property: extremely strong spin-orbit coupling. In simple terms, the spin of electrons, a quantum property like rotation, is tightly linked to their motion around the nucleus, and that opens the door to something revolutionary. While silicon controls electrons only by charge, bismuth lets us control spin as well. That changes the game. Instead of simply switching a current on or off, we're talking about quantum-level processing on a chip. This could lead to new types of transistors, memories, even qubits. But there's a catch. Bismuth naturally has no bandgap, which makes it act like a metal. Without a bandgap, there's no switching, and without switching, there's no logic. End of the road? Not exactly. There's a solution: doping, adding other elements to change its electronic structure. And that's exactly what a Chinese team did. For the first time in history, they created a functional semiconductor based on bismuth, the world's first silicon-free chip. This breakthrough happened at Peking University, published in Nature. The researchers doped bismuth with tellurium and built the first functional silicon-free chip layer by layer. And they went further. This wasn't just proof of concept. The chip was fabricated at the angstrom scale, even smaller than 2 nanometers. Parts of the transistor measured just 0.5 nanometers thick, smaller than a silicon atom. At that scale, silicon collapses under quantum effects. But with bismuth, those barriers seem to disappear. Tests showed that the doped bismuth chip could run at frequencies above 500 GHz. For comparison, top Intel, Apple, and Samsung chips max out around 5 to 6 GHz. This prototype hit more than 500. It also consumed 3 times less energy and switched 40% faster. These comparisons were made against real Intel, TSMC, and Samsung transistors, and bismuth won on every front. But bismuth didn't act alone. To connect the transistors, engineers used graphene, the thinnest, lightest, strongest material we know. A conductor so efficient it enables microscopic connections with nearly zero loss. The result? A fully silicon-free chip with bismuth transistors and graphene interconnects built layer by atomic layer. Still, building it was an enormous challenge. The chosen design, gate all around, wraps the transistor channel completely with the control electrode. That requires atomic precision. Imagine making a sheet just 0.5 nanometers thick. then wrapping it in another sheet just as thin. This was only possible by alternating bismuth and graphene layers, stacking up to 4 transistors in one block. For support, they used a silicon base, but only as mechanical scaffolding. No active silicon. This was the birth of a new kind of electronics, with colorful crystal and pure carbon replacing what powered the world for decades. And the results are clear. The bismuth chip outperformed the giants in 3 critical areas: speed, energy efficiency, and leakage control. These 3 variables define the future of processors, and more than that, they define who will lead the next digital revolution. In this race, China has taken the lead. The pioneering study came from Beijing, and China controls over 70% of the world's bismuth reserves. A resource once considered a curiosity is now becoming strategic. If this technology scales, whoever controls bismuth controls the next leap in computing. It's no coincidence that TSMC is already moving. In partnership with MIT and Taiwan National University, TSMC has started testing bismuth as a contact material for next-gen transistors. The shift has begun, and there's no going back. This kind of material revolution is nothing new. It happened with copper, with silicon, with germanium, and now with bismuth. And while engineers reinvent the hardware foundation, another transformation is unfolding in software. The rise of artificial intelligence as a tool for creation, analysis, and automation. The post-silicon era has begun, but it's still in the lab. Despite the progress, this isn't a consumer product yet. The bismuth chip is a prototype. It works, it beats benchmarks, but the ecosystem isn't ready. Producing ultra-pure doped bismuth, layering with atomic precision, aligning graphene at industrial scale, these are challenges far from silicon's mature, optimized ecosystem. Silicon has decades of standardization, dedicated equipment, supply chains, refining, and fabs. Bismuth is still crawling. Adapting would require new machines, processes, and likely new factories. That takes money and time. Like past revolutions, this one will start small. Academic labs, defense prototypes, until suddenly someone figures out how to scale. And when that happens, the market will shift as dramatically as it did when we left vacuum tubes behind for transistors. The question isn't whether silicon will be replaced. The question is, who will be the first to turn this into industrial dominance? The future is being written in crystals and atoms, bismuth, graphene, vertical architectures, frequencies beyond 500 GHz. We're no longer talking about gradual evolution. We're witnessing the beginning of a new paradigm. Just as silicon replaced germanium and chips replaced vacuum tubes, these new materials could unlock possibilities we can't yet imagine: faster, thinner, smarter, maybe even more aware. But no revolution happens alone, and no technology is born perfect. Bismuth's success now depends on more than labs. It depends on industry, investment, engineering, politics, and time. And, like all great turning points, it may also depend on who's paying attention when the tectonic plates of the market begin to move. So tell me, do you think silicon will survive another decade, or are we already watching the birth of its successor? Share your opinion in the comments. And if this video gave you a new perspective, like and share. It helps the channel keep bringing this kind of deep content.